Hello, chemistry. Today, our goal is to do these notes that have to do with why reactions are exothermic, some reactions are exothermic, and other reactions are endothermic. So to try to get at that answer there, one thing we need to think about is breaking bonds and making bonds. And one thing that you absolutely must understand is that breaking bonds is always endothermic. So we want to think about why is that the case. So first, let's just think about say two hydrogen atoms bonded to each other. That bond really means that the two hydrogen atoms are attracted to each other. Why are they attracted to each other? If you remember, the bond is really the shared electrons. And so you have a nucleus for each hydrogen atom, and then you have these two shared electrons that are in between. So obviously the nuclei are both attracted to those shared electrons. So if you're going to pull the hydrogen atoms apart from each other, you're going to have to break that attraction. So it's endothermic because energy must be absorbed to break the attraction, right? You're going to must pull apart. They're attracted to each other. So you're going to put in energy and use that energy to pull them apart. So that's going to be endothermic. It has to absorb, the reaction has to basically absorb energy to pull apart those hydrogen atoms. Making bonds is exothermic, so it's releasing heat. So that's like a favored change, right? Exothermic is a favored reaction. And so what happens? Say you have your hydrogen atom and your other hydrogen atom, and they're pretty far away, but as they get closer to each other, you're going to start getting that attraction between the nuclei and the shared electrons. And so then once you get that attraction, it's going to pull them together. So making bonds is favored and you're forming this attraction. It's like two magnets. They're going to want to come together, right? So making bonds, you make the attraction and it's favored. It's going to just happen on its own, right? You make the attraction. They come together on own, right? You don't have to put in any energy. You just get them as they get close to each other. They're going to be attracted and they're going to pull each other together. So that's going to be our exothermic situation. So make sure you got it. Breaking bonds is endothermic. Pull them apart. Making bonds is exothermic. They're going to come together and attract. Okay, so let's look at a couple situations where you're going to be making and breaking bonds. So first ones that are really easy are these phase changes. In phase changes, they're either breaking bonds or making bonds. So in this graph over here, you can see we have melting, which is from solid to liquid. And then you can go liquid to gas, and that's vaporization. Or you could go directly solid all the way to gas, and that would be sublimation. All three of those situations are endothermic. You can see they're going uphill, and so they're endothermic. So why is that? Why are they endothermic? You're always breaking bonds when you do these phase changes, right? Melting is solid to liquid. You're going to break bonds. Vaporization is liquid to gas. You're going to have to break bonds to do that. And sublimation is solid all the way to gas. So all of these changes, you must break bonds. Now, what bonds are we going to be breaking if you're just making phase changes? They're not chemical bonds, right? These are attractions between our molecules. If it was water, it would be hydrogen bonds that you would be breaking. They might be dipole-dipole. They might be dispersion attractions. If it was an ionic, you would break ionic bonds between them. So you must break bonds for these phase change. All right? And when we say break bonds, these are going to be probably intermolecular forces that are being broken. So for condensation, freezing, and deposition, all of those are where you're making bonds, right? Condensation is gas to liquid. You're going to have to make attractions between your molecules so as they come closer together. Freezing liquid to solid, you're going to have to make bonds, and deposition is gas to solid. So all of these is situations where you're going to make bonds, must make bonds, and so that is going to be exothermic. Okay, and again, making the bonds, it would depend on what it is. It might be intermolecular, it might be ionic. Those are the attractions that you're going to be making. So phase changes are pretty simple because you either, in any phase change, you're either going to be making bonds or breaking bonds, but you don't do both, right? You're either going to make or break. But now when we do chemical reactions, they're a little bit more complicated because in a chemical reaction, usually you're going to have to break some bonds of the reactants, and then you're going to have to form some new bonds in the products. So it's a little bit more complicated. You're going to make and you're going to break. Okay. So let's look at a very simple reaction here, the combustion of hydrogen. So we're going to take hydrogen gas, we're going to react with oxygen gas to form water. So here's our reaction, hydrogen gas plus oxygen gas to go to water vapor. And you can see the reactions that we have, our molecules. We have our two H2 molecules, they're an O2, and we form two water molecules. So you want to think about, well, what has to happen to get that reaction to occur? Well, we're going to have to break these bonds between the two hydrogen atoms in each hydrogen molecule. You're going to need to break that double bond between the two oxygens, but then you're going to be making all of these oxygen to hydrogen bonds in the water molecule. So there's going to be 4 of those. And so you're going to need to break bonds, and then you're going to make the bonds as well. And so when we break the bonds, that's going to be endothermic. So we're going uphill and we're breaking the bonds. And then when we make these bonds here, we're going to form our bonds, which is going to be exothermic. And in this particular reaction, it happens to be exothermic. And so the diagram is showing you that you're going to go up to break bonds, but when you go down and have exothermic, the bond forming is like a bigger energy change. And so the net change between here and here, the net delta H is going to be a negative delta H, and it's going to be exothermic. So we're going to do a reaction. We're going to actually add up what is that delta H for the reaction. But first, let me just show you the reaction. So it's a pretty nice reaction. Obviously, it's pretty exothermic. It releases lots of heat. And so I have a little video that we can watch really quick. So here we go. This is a professor who had all 4 of these balloons are filled with hydrogen gas. So let me play this video here.
The great enemy of writing,
sorry about that,
isn't your own lack of talent, it's being interrupted.
Sorry about that. Here we go. Here's the video. So all the balloons are filled with hydrogen gas. He just has his so definitely very exothermic. You get a nice sound, and obviously you can see that flame that was formed. Now here he has another balloon, and he actually filled it with hydrogen gas and oxygen gas, and he filled it with the right ratio. So there's 2 parts hydrogen to 1 part oxygen. So let's see that one.
If that sound was too loud for you, keep your mouth open, because then the pressure in your mouth
There we go. We know that's much, much louder. Okay, so let's go back to our notes. So anyway, the reaction is very exothermic, releases lots of heat. And so the reason is because the energy it takes to break the bonds is not as much as the energy that you get back when you form the bonds, right? So remember, it's endothermic here, positive delta H to break all the bonds. So we're imagining we're going to break all those bonds, and then you're going to make all the new bonds between the hydrogen and oxygens, and it must be that you're getting more energy back. It's releasing more energy than what it absorbed, and so the net change is negative delta H. I mean, the bond forming is also negative delta H, but that difference is going to be our overall reaction delta H. So let's see if we can actually get the numbers of how much energy it takes to break the bonds and how much energy is released when the bonds form. So again, in this reaction, we're going to break two bonds between the hydrogen to the hydrogen bond. So what we're going to do, we're going to look up on this energy, bond energy chart, and it's telling us it takes 436 kilojoules of heat to break the bond for a mole of hydrogen-hydrogen bonds, right? So you have a mole of these bonds. That's how much energy it takes. Right? So again, it's endothermic to break them, so it's the amount of energy it takes to break the bond. So what we're going to do is we're going to do 2 times the 436, and we don't have to write in the kilojoules per mole. So I'm just going to write above it that that's the H to H bonds. So we have 2 of those. So we're going to break those, and then we're going to break 1 of the oxygen-oxygen bond. And in this case, it's an oxygen double bond O, right? So you're breaking the whole thing. You're breaking the whole double bond. So 498 kilojoules to break that one double bond there. Okay, so we just need to calculate that. Okay, and I got 1370 kilojoules per mole for breaking. And notice we know that's going to be endothermic. So I'm just going to put in that positive to be extra clear that I know that's a positive endothermic change there. Endo. So now we're going to make the bonds that we need. And obviously we're going to make hydrogen to oxygen single bonds, and we're going to need 4 of those. So the hydrogen oxygen single bonds are 467. So we're going to do 4 times 467. And you will get 1868. Now, we are making the bonds here, and so we need to change this and make it negative. We need it to be exothermic. So I'm going to put in the negative in front of there, kilojoules per mole. So it takes 1370 to break the bonds, and then you release 1868. When you make the bonds. And so the net change is going to be negative. So really what you're going to do is you're going to add the 1370 plus the negative 1868. So you're really adding them together, add that, and you get your value of negative 498 kilojoules per mole. So that's going to be our delta H for the overall reaction. So that's that value right there. All right, go up 1370, and then you're going to go down negative 1868, and that net change is the negative 498 kilojoules per mole. So that's the delta H, and it is coming out negative. It's exothermic, so that makes sense. So now let's look at the opposite. If you now do the electrolysis of water, what you're going to do is you're going to start with all water, and you can send electricity through the water, and it breaks it down into hydrogen gas and oxygen gas. This is the exact opposite of the burning of the hydrogen. And so if this one is exothermic, this one should be endothermic. Let me just show you, this is a picture of the little Hoffman apparatus. Let me just show you. You've seen it in class as well, but let me show you this one just so you can see. You set up a little Hoffman apparatus. You've got some water in
all the way to the top here
in the test tubes, and then he's just connecting.
In each of those. So
he's just connecting his electrodes to the battery. So you have a battery. The battery is going to put in electricity, and you can see immediately that you get gases forming in both test tubes there. So one of those is hydrogen gas and one is oxygen gas. And so you can collect those gases. So this is electrolysis, which we've seen before. All right, so let's go back and look at our notes. And so now when you do your calculation, it would be exactly the same calculation that you did before, but it's really just the opposite, right? The bond breaking is going to be the 4 of the HO bonds, which is the 467 kilojoules per mole, which is the HO bond. And we're breaking them though this time, and so we're going to get positive 1868 kilojoules. And now with the making, we're going to get the same making that we broke before. So it was the same 2 times the 436 plus 1 of the 498. So you're going to break 2 of the hydrogen-hydrogen bonds and then the 1 double bond O-O bond. And in this case, though, now we're making those bonds. So those are going to be negative values. And we're going to end up with our negative 1370 kilojoules. So once again, this is going to be our endo, and this is our exo. So really, we just switched places. So now the endothermic change, when we're breaking the bonds, is the bigger change. So we have our delta H is equal to positive 1868. And then when you make the bonds, exothermic, negative delta H is negative 1370 kilojoules per mole. So you can see you have to put in more energy than what you get out. So when you add these two together, obviously we get the same answer as before, but this time it's positive. So it's exactly the same value, it's just the exact opposite because we're doing the reaction in the opposite direction. There we go. One thing I want to point out, so when it takes more energy to break the bonds, that means those bonds are stronger than the bonds that you're making at the end. So in this case, we can think of the reactants were really hard to break apart. So these have the stronger bonds. You can think of the molecules as being more stable. Molecules, more stable. And then you're forming products that have weaker bonds. Or you could say that they are less stable molecules. So that's a good way to think about the differences between your exo and your endothermic reactions. So obviously it would be the opposite up above here. The reactants, it took less energy to break than what you got back when you made them. So these are going to be your weaker bonds. So really the bonds between the hydrogens and the oxygen there were weaker, and the products had stronger bonds. So that H to O bond in the water are the stronger bonds. Okay, more stable. So you always go from less stable to more stable is the favored direction. And then so for exo and then for endo, more stable to less stable. Okay, and it's not the favored direction. All right, so let's do one more example and then we're done. So here I have another reaction. This is the combustion of methane. This is just the natural gas that would come out of your gas jets. And so this time now I'm giving you the overall reaction. It is balanced, but we need to know what bonds are breaking and what bonds are forming. And so let's write out our Lewis dot. So put the carbon in the center. We have our 4 hydrogen atoms. We need to add up our total number of electrons. Carbon's 4, each hydrogen's 1, so that's a total of 8 electrons. And so I'm going to put in my single bonds, 2, 4, 6, 8. I now have an octet around the carbon. I have my duets around the hydrogen. That is my Lewis dot for CH4. Next, I need to do O2. So you probably know what O2 looks like, but if you want to do the Lewis dot one more time, each oxygen has 6 electrons. So that's going to be a total of 12. So 2, 4, 6, 8, 10, 12. Look for octets. Obviously, this oxygen needs an octet. We're going to take 2, and we make our O2 molecule. You would do that again because you would need 2 of them. So now we have our Lewis dots for our 2 O2s. And then we're going to do a similar thing for CO2. CO2, we've got carbon in the center, oxygen, oxygen. If you add up all your electrons and do your Lewis dot, you should come out that there's 2 double bonds and then your 2 lone pairs on the CO2. So you get one of those, and then waters. Obviously, we know our Lewis dot for water at this point, and we need 2 of them. So I'll just write another one in. All right? Okay. So it's important to write the Lewis dots because you need to be able to figure out what bonds are breaking and what bonds are forming. So in this situation, what bonds are going to be breaking? We're going to need to break all 4 of these carbon-hydrogen bonds, and we're also going to need to break both of these oxygen-oxygen double bonds. So we need to get information on what those bond energies are. So at the bottom of this page, we have some charts which has some bond energies for you. So this first one is all single bonds, and so we need carbon to hydrogen. So you can look here, here's hydrogen, and here's carbon. So hydrogen and carbon bond is 416. So let's fill that in up top. So we're going to need 4 of those that we need to break. So 4 times the 416, and it's going to be endothermic, right? So positive value. And then we're going to break 2 of the oxygen-oxygen bonds that are double bonds between the oxygen. So make sure you don't choose this oxygen to oxygen bond because that would be a single bond between 2 oxygens. So the ones that are double bonds are down here at the bottom, and we need the oxygen-oxygen double bond, and it specifically is the one that is in O2, 498, and that's what we had on the front of the lab too. So sorry about that. So let's write in 498. All right, so we just need to calculate that. Okay, so I got 1664 for that part, and then 996 here. So if you add all that up, I got positive 2660, and that is in kilojoules. Oh, get rid of that. We're going to do kilojoules per mole. And okay, so I think we're set. That is what we're going to break, and now we're going to have to make. So to make, we're going to make 2 of the carbon-oxygen double bond. So we're going to do 2 times the carbon-oxygen double bond, which was the one down here. We need, now there's 2 different carbon to oxygen bonds. CO2 is such a common substance that the value is exactly 803. When you have carbon to oxygen in other molecules, it's slightly different. And so for any other molecules that have carbon to oxygen double bonds, we're going to use 695. But if it's CO2, use the more exact value of 803. All right, so let's do that. So we are going to make 2 of them negative 803. We're making, so again, I'm making it negative. And now we need to make 4 of the hydrogen to oxygen bonds. So 4 hydrogen to oxygen, that again is a single bond. Hydrogen to oxygen, we've done that one before, and so that's the 467. Okay, so 467, let's calculate all that. Okay, oops, I forgot my negative, so let me get that in there. Just move that over. So we definitely need the negative. When you calculate, I got negative 1606 here, and I got negative 1868 here, giving me a total of negative 3474, all in kilojoules. We're now going to add up the 2. So we need the 2660, add the negative 3474, obviously is coming out negative, and I got negative 814, that is kilojoules per mole. So that is our delta H for this reaction. It is the combustion of methane, and so we know that's going to be exothermic, so that makes sense. Okay, so just really quick, let's make a quick diagram. So the concept is that we know it's exothermic overall, and we know that it took less energy to go up and more energy when you went down. So overall, it's a net downhill. So I'm going to start kind of maybe around here, and these are going to be our reactants. So this is going to be our CH4 and our 2 O2s. And I know at the end, I'm going to end out lower down here somewhere. So I'm just going to show that we're going to go up first, right? This is going to be the delta H of breaking our bonds, and that's going to be positive value. So up here are going to be our separate atoms, as we broke everything apart, right? We broke all the carbons, hydrogens apart. We broke both oxygens apart. So we've got all separate atoms on the top. And then we're going to go down for the making. So this is our delta H for making our bonds. And so let's plug in our values. So the breaking delta H was positive 2660, and the making was negative 3474. And so that net change here that goes from reactants to products is our delta H of the reaction, and that comes out as our negative 814 for our delta H of the reaction, right? So there you go. That's the kind of energy diagram I want you to be able to do. So you're seeing that you're going up to break, and then you're going down to make, and then you're seeing what that change is. So this is an exothermic looking diagram where you have the reactants, and then overall products is lower. But remember, endothermic, it would have the products up higher. So some reactions would be exo, and some are going to be endo. So that's what you need to be able to do for the homework. You're going to use this chart here for your homework, so make sure you have this available. Let me just pull up the homework really quick. I just want to warn you, you just have this one page. You're going to be figuring out the delta H of each of these reactions. You're going to have your diagrams over here. We're not going to do them in kilocalories, as it says. We're going to change that to kilojoules for all of them. You can change this one to kilojoules too. And then I think other than that, you're in good shape. Okay, so don't forget, especially some of them, you have to do your Lewis dot. So make sure you know what your Lewis dot looks like. So in this case, it's not a single bond. So make sure you're getting the right Lewis dot for your N2 gas. That's it for now.